Just started recording. Um, anyway, when we talk about resolution, it's going to be the average mass of the two peaks that we're interested in separating, divided by the difference between those peaks. Right? So when we look at a mass spectrum, whenever we think about resolution, we're always thinking about a peak and its neighbor, right? We would never talk about the resolution between this peak and this peak, because there's two peaks in between. Who cares what the resolution is between those two? And so we're always going to be talking about, resolution of neighboring peaks. And when we go and calculate our resolution, it's going to be the average mass divided by that difference in mass. And so the thing that most instruments actually do pretty well is maintain resolution in terms of that difference, right? And so if I'm able to, change, if I'm able to have one mass number accuracy, right? Remember we saw when we did the tuning in lab on Tuesday, how we saw the peak and then we saw the little isotope peak. Remember this? Okay. That isotope peak didn't quite go all the way down the baseline on our instrument, but it went about as close to the baseline for the peak at 70 as it did for the peak at 210, as it did for the peak at 580 or whatever it was, right? And so sort of the resolution between two masses, how well it gets down the baseline is about the same. So that delta M is usually the same for instruments, but of course that changes the resolution based on what masses we're talking about. Right? If our delta M is always 1, the resolution at M over Z of 100 is 100. If the resolution at M over Z of 1,000 is 1,000, right? And so this resolution changes with the mass. And so when we talk about instrument resolution, most of the time, they're going to talk about resolution somewhere around the 200 M over Z range, right? It's not a set thing. And so when they talk about resolution, you got to kind of think about it. Okay, what are we resolving at what masses? And so different mass analyzers have different resolutions. We'll talk a little bit about that. The one, we're not talking about one mass analyzer because it's on our list of possible topics at the end of the year. And that's the FTICR, so Fourier transform ion cyclotron resonance mass spec. It's a mouthful, but it's the highest resolution out there, right? And it's a neat instrument in that it can measure both positive and negative ions simultaneously. And so there's a spectrum, and I've looked for it, and I can't find the paper that it's in, but I saw it when I was in grad school taking a mass spec class. The paper looks like this. Here's a peak that's very narrow, and here's a peak that's very narrow. There's a whole lot of baseline between them, right? This Cl plus, this Cl minus, right? So the difference of 2 electrons, and they're that well separated. Right? And so it's not uncommon for you to have resolutions of 1 million or 10 million on an FTIC-RMS. Okay. All right, so what are some of these mass analyzers that we can talk about? Well, the first is this quadrupole mass analyzer. Right? And so you have these 4 poles, right? Again, that's not why it's called quadrupole. It's because of the field that's generated. But you have this field, and that field is operating at a certain radio frequency, a certain RF frequency, right? And so let's say that these two rods are connected, and that these two rods are connected. And so one of these will be a plus and one of these will be a minus. And you'll have some RF frequency, which also have some DC voltage applied. And whatever ions are resonant with that frequency will make it through. It could be one ion, it could be a whole lot of ions. Any ions that are not resonant with that frequency will start to lose their resonance, and they'll get ejected out of that ion trap. Okay, so RF and DC applied to opposing pairs. Okay. Going along with this is a linear, right? Quadrupole. We also have that 3D quadrupole. And in it, you have your end cap and your end cap. So you have your two end caps. Right? And your two end caps have very similar voltages. They behave as one pair of those rods. And then this ring electrode, in this cutaway, you can see that to the atoms, to the molecules in the middle, in this dimension at least, it looks like it's two electrodes, even though physically it's one sort of donut electrode. Right? And so what it does is it compresses them not only in one dimension but in every dimension, and so they're sort of formed in this nice little point in the middle. And so it holds fewer ions than a linear quadrupole trap, but it's also much more compact. And so your ions come in, they're held here, and as they're being held there, you can change the RF and the DC, and the ones that are still resonant will just stay in the trap, and the ones that aren't resonant will get ejected. In the previous slide, it was easy to see, this resonance is as they move down the trap. In a 3D trap, they're, moving sort of in a circle at some resonant frequency, right? And so they always sort of follow the same exact path. If they're non-resonant, then they might follow the path for a while, but then they don't match up the second time, right? And so they're not on the same path, and eventually they'll work their way out of the trap. Right? And so the green not resonant, the blue resonant in that case. All right, and we saw both of those in lab. How these work is based on this Matthews stability diagram. And so the Q here is our RF, is based on RF. A is based on DC. Right? And so if we want to isolate a particular M over Z, then we can set our DC and our RF to be those exact values. Right? If we wanted to isolate a wider range of masses, then we could change our DC. Right? We could lower our DC, and then as we scan our RF, we'd be down there. Or we could cut our DC off completely, and we'd have the widest range of masses be stable. Right? And so if you just wanted to get all the ions out, cut off your DC, and then everything is stable. Right? If you wanted to isolate a single ion, turn your DC on and set your RF frequency, and you would be right there. This isn't in the textbook. It's just a little extra. But that's all the time we have for today. I hope you have a joyous weekend. Relax. We only have 4 more weeks of lecture and a week of oral reports.
Dr. Davis, I have a quick question.
Yes, sir.
Back on the slide with the mass analyzer's resolution, the closer the like on the bottom where with the CL plus and CL minus, is that a worse resolution because they're farther apart?
No. Yeah, this is they're farther apart in space, but this distance is very, very small, right? This is just the mass of 2 electrons. And so, the delta is super tiny here. Even though it looks like they're farther apart, the delta M is very, very small. It's about 0.0018 for 2 electrons.
Okay.
Okay. Tata.
Hi, thank you.
Yeah.
Dr. Davis, can we ask you a quick question?
Ask me a quick question.
You mute yourself and talk on here. I was worried he's gonna get away. So worried. Shy get in. Okay. We were working on the math